Welcome back to Applied AI Engineer. Last episode we built Atlas V1, a working retrieval augmented assistant over our toy store's documents. But it had a dirty secret. Its memory was a Python list we re-embedded from scratch on every single run. Fine for a demo, hopeless for production. Today we fix it. We move Atlas onto a real, persistent vector database, add metadata filtering so search respects your business rules, and build a hybrid retriever that fuses keyword and semantic search. By the end, Atlas remembers between runs and retrieves like a grown-up. Quick recap of where episode 6 left Atlas. We had the full RAG pipeline, load the documents, split them into chunks, embed each chunk, store the vectors, retrieve the closest ones to a question, paste them into the prompt, and generate a grounded answer. It worked, but the storage was a throwaway list living in RAM. Restart the process and everything's gone, re-embedded from zero. Three things are missing for production: persistence, the ability to filter by metadata, and exact keyword matching. That's our whole agenda. So what does a real vector database actually buy us? 4 things. First, persistence. You embed your corpus once, write it to disk, and every later process opens it instantly. Second, fast approximate nearest neighbor search, so finding the closest vectors stays quick even across millions of them. Third, it stores metadata right beside each vector, which unlocks filtering. And fourth, it gives you upserts keyed by ID, so reindexing a changed document updates it in place instead of creating a duplicate. Those 4 are the difference between a notebook and a service. There's a small zoo of options, but they share one mental model. Chroma is embedded, it runs inside your process and persists to a local folder, 0 servers, which is why we use it here. PageVector puts vectors right inside Postgres, so your app data and your search index live in one database. Wonderful if you already run Postgres. Face is a raw, blazing fast similarity library, but you handle persistence and metadata yourself. And Pinecone is fully managed in the cloud. You hand over the operations and pay a bill. Same concepts, different trade-offs. Let's start with the most important upgrade, making the store survive a restart. We'll define our chunks with stable identities and metadata, embed them locally, and write them to disk with Chroma. From then on, Atlas opens an existing index instead of rebuilding it. Here's the foundational change. In episode 6, a chunk was just a string. Now every chunk carries a stable ID, prod rover, policy returns, and a little dictionary of metadata, category, recommended age, price. The ID is what makes upserts idempotent later, and that metadata is exactly what we'll filter on. The asLists helper just unzips our documents into the 3 parallel lists Chroma expects: IDs, documents, and metadatas. Same content as before, now it has structure. We'll embed with a local model so this whole episode runs with no API key. Sentence transformers gives us All-Minion, a small but capable model that returns 384-dimensional vectors right on your machine. We wrap it in one embed function and load the model exactly once, as a module-level singleton. The crucial rule: queries and documents must pass through the identical function, or their vectors won't live in the same space. And just like our LLM adapter in episode 1, swapping to Voyage or OpenAI later is a one-function change. Now the database itself. A persistent client points at a folder, here, Atlas_DB, and that's where Chroma writes everything: the vectors, the documents, the metadata, and the search index. Get or create collection either makes the collection the first time or opens the existing one on every run after. We tell it to use cosine distance, which matches our normalized embeddings. Notice we import embed before Chroma. On Windows, the native libraries must initialize in that order, a small but real production gotcha. And here's indexing. We embed the documents ourselves and hand the vectors to upsert, alongside the IDs, the raw text, and the metadata. Upsert is the verb that matters, because our IDs are stable. Running this again doesn't duplicate anything, it overwrites each chunk in place. Change a product description, rerun build, and only that one chunk updates. This single method replaces episode 6's rebuild the entire store on every boot. Let's run it and confirm the chunks land on disk. 10 chunks embedded and written into a folder called atlas_db, and the collection reports 10 vectors. The important part is what happens next time. If I run this again, it reuses the same on-disk index, no re-embedding, no waiting. Atlas now has durable memory. Restart the machine and the knowledge base is still there, ready to query in milliseconds. Here's the whole indexing path in one picture. Each chunk, with its ID and metadata, goes through the local embedded to become a 384-dimensional vector. We upsert that into the Chroma store, which writes it to disk along with the document text and the HNSW search index. From then on, a query just embeds the question and asks the store for the nearest vectors. Embed once on the left, query forever on the right. And because IDs are stable, upsert updates in place rather than duplicating. Pure semantic search finds what a question means, but real products also have hard constraints. Only show toys under $40. Only return support documents. That's metadata filtering, and a vector DB makes it one clean argument instead of a pile of Python. Why does this matter? Because meaning and rules are different things. A vector tells you a chunk is about building toys. It can't tell you the price is under $40 or the category is exactly support. Those are structured constraints. Chroma lets you pass a where clause that runs as a pre-filter. It discards every chunk whose metadata doesn't match, then ranks only the survivors. That's cheaper and safer than fetching everything and filtering afterwards in Python, where you might run out of results. The operators read like Mongo, equals, greater than, less than, in, combined with, and or. The code barely changes. We embed the query, call collection.query, and the only new argument is where. Chroma returns parallel lists, IDs, documents, metadatas, and distances, which we zip together. One detail worth burning in, the database hands back a distance, and since we're in cosine space, the similarity is simply 1 minus that distance. Higher similarity, closer match. Now let's run the same question with and without a filter and watch the result set shrink to exactly what's allowed. Same natural language question both times. The first call is unconstrained, pure semantics across all 10 chunks. The second adds a where clause that says, category must be building and price must be under $40 combined with $end. So even if a $90 robotics kit is semantically relevant, it's filtered out before ranking. This is how you respect a user's budget or a category page while still getting the smart, meaning-based ordering. Watch the difference. Look at the two result sets. Unfiltered, the top 3 mix categories gears, then a robotics car, then an electronics kit because all three are semantically near the query. But the moment we filter to building toys under $40, the robotics kits vanish entirely and we're left with only gears and blocks, the two chunks that satisfy both the meaning and the rules. The scores are real cosine similarities. The filter changed which chunks were even eligible. That's structured search and semantic search working together. Here's the order of operations, which trips people up. The filter is not applied after ranking, it's applied before. The database starts with all 10 chunks. The where clause keeps only the ones matching category and price, and just those two survivors get scored by cosine similarity. The out-of-scope chunks are never even compared. That's why filtering in the database beats fetching the top K, and filtering in Python, you'd risk throwing away your whole result set and being left with nothing. Dense vectors are brilliant at meaning, but they have a blind spot: exact terms. A product code, a proper name, a rare word, vectors can blur those. The classic keyword algorithm, BM25, is the opposite. The professional move is to use both and fuse their scores. That's hybrid search. Think of it as two specialists. The dense retriever, our vectors, is great at paraphrase. Ask about machines that move and it finds the gaze set even though those words never appear. BM25, the sparse retriever, is a keyword expert. It nails an exact token like a SKU or the name roverbot, which a vector might smear into nearby concepts. Each has a failure mode the other covers. So instead of betting on one, we run both and fuse their scores into a single ranking. In production RAG, hybrid is very often the default, not a luxury. The sparse side is refreshingly simple. We tokenize every chunk, just lowercase, and split, and hand the tokens to BM25 Okapi, which builds a classic keyword index from term frequencies. No model, no GPU, no embedding, it's pure term statistics. The one helper that matters is min-max scaling. BM25 scores and cosine scores live on completely different scales, so before we can blend them we squeeze each ranker's scores into a 0 to 1 range. That makes the two comparable. Here's the fusion. We score every chunk both ways, BM25 keywords and Chroma cosine, normalize each set, then blend them with a single weighted sum. Alpha is the dial, at 1 it's pure dense, at 0 it's pure BM25, and in the middle it's a blend. We sort by the fused score and take the top K. This particular recipe is called weighted score fusion. You'll also meet reciprocal rank fusion, which blends ranks instead of scores. Either way the idea is identical. Let two opinions vote on one ranking. This is the lesson in one table. The true answer is the circuit lab. It's the electronics kit with a radio and an alarm. Dense search gets it right, prod circuit on top. But BM25 alone is fooled. The words snap together also appear in the roverbot description, so the keyword ranker pushes roverbot to the top and buries the correct chunk down at third. Now look at the hybrid blend. Prod circuit climbs back up to a near tie at the top, 0.702 against 0.72. The dense signal rescues the answer that keywords alone got wrong. Neither retriever is perfect fused. They cover each other's mistakes. Here's hybrid search as a shape. The query fans out to two retrievers in parallel, BM25 on the left scoring exact keywords, dense vectors on the right scoring meaning. Each produces its own ranking on its own scale, so we normalize both to 0 to 1. Then we fuse them with the alpha weighted sum. alpha times dense plus 1 minus alpha times BM25, and that single combined score decides the final order. 2 opinions in, 1 ranked list out. Tune alpha to your corpus, keyword-heavy data leans low, conceptual questions lean high. We've upgraded the retriever in isolation. The payoff is dropping it straight back into the RAG pipeline from episode 6. The beautiful part, only the retrieval layer changed. The prompt, the grounding rules, and the model call are exactly as they were. Here's Atlas version 2. We retrieve with the hybrid search we just built, format each chunk with its ID in brackets, and paste that context into a grounded prompt, one that forbids outside knowledge and demands the model cite the chunk IDs it used. Then we call the very same chat adapter from episode 1. That's the whole point of building a clean retrieval layer and a clean generation scene. We swapped the toy in-memory store for a persistent, filtered, hybrid retriever, and the generation code didn't move an inch. And here's Atlas v2 answering a real, multi-hop question. I opened my roverbot kit 10 days ago. Can I still return it? The hybrid retriever pulls the returns policy, and the roverbot product chunk, it has to combine both to reason. And the answer is correct and grounded. It identifies roverbot as a robotics kit, applies the 14-day opened electronics window, and concludes 10 days is still inside it, citing the policy chunk it relied on. That citation is what makes the answer auditable. This is a genuine reply from the model over our retrieved context. Step back and look at the assembled system. A question comes in and hits the hybrid retriever, BM25 plus dense vectors, over the persistent Chroma store, with metadata filtering available. The top chunks flow into the grounded prompt, which goes to LLM.chat and comes back as a cited answer. Compare this to episode 6's diagram, and only one box changed color, the retriever. Everything downstream is untouched. That's what good scenes give you. You can make retrieval dramatically smarter without rewriting the app around it. One last orientation, because you won't always use Chroma. The concepts transfer directly. In pgvector you write SQL order by the distance operator, limit k, with an ordinary where clause for your filter. Pinecone and Viviate expose the same query plus filter plus hybrid shape over HTTP. And frameworks like LangChain and LlamaIndex wrap every one of them behind a single retriever interface, so switching databases is a config change, not a rewrite. Your embeddings stay swappable to local mini-LM today, a hosted model tomorrow. Learn the pattern once, it pays out across the whole ecosystem. Let's recap. Atlas now lives in a persistent vector database. We embed once, upsert by stable ID, and the index survives restarts. We can filter by metadata, applying hard business rules as a pre-filter before ranking. And we built a hybrid retriever that fuses BM25's keyword precision with dense vectors' grasp of meaning, balanced by one tunable knob. Crucially, only the retrieval layer changed, the prompt and the model call stayed exactly where they were. Next episode we push retrieval quality even further, advanced RAG, re-ranking with a cross-encoder, rewriting queries, adding proper citations, and learning to say I don't know gracefully. See you there.